Question 5, we've got the records of a high jump, h metres, achieved by students distributed with a mean of 1.4 metres and a standard deviation of 0.15. Part A, simply we're going to find the proportion of the students achieving a height of more than 1.6 metres. So here's the distribution. So if you plug in 1.6 metres being the lower limit and 999 the upper limit, with both mu and sigma, and this turns out to be 0.0912. And that's the answer to part A. We now switch to the 1500 metres, again normally distributed, this time with a mean of 330 seconds and a standard deviation of 26 seconds. So let's write that down first of all. So the head wants to know the probability of a student who can not only satisfy this requirement of jumping higher than 1.6 metres and can run the 1500 metres in a time of less than 5 minutes. So we need to work downwards from 300 seconds. So preparing for the calculator, our lower limit is negative 999 and our upper limit is 300. Put those in with the mean and the standard deviation and you get a probability, and this is equal to 0.1243. So the probability of student achieving the high jump and the 1500 metres will be the multiplication of these two results. And this turns out to be 0.0113. And I've made a bit of an error because I've answered part C of the question before part B. We've got to state a necessary assumption about H and T for the head to calculate and achieve this answer. Well, for this answer to be correct, the same pupils must be involved in both the high jump and the 1500 metres. Because if you've got a completely different set of students attempting now the 1500 metres, all of this calculation would be void. So I've just got to write that down. So there it is written down, and I've also included that the results must be independent. And what that means is that the performance in the high jump must not in any way affect the performance in the 1500 metres. So there we are. That's the answer to part B, squeezed in between A and C. And so in part D, we move to the discus. The discus results also normally distributed, but we don't know both the mean or the standard deviation. All we are given are two areas, two probabilities with the corresponding d-values. So because we don't know both the mean and the standard deviation, we have to do this via simultaneous equations, and we have to go via Z, the standard normal distribution, and then use this formula, which is Z is equal to D minus mu over sigma, to get back to both the mean value and the standard deviation. Okay. So let's set up two columns. So to get the Z value, we have to make the mean is equal to 0 and sigma is equal to 1. Put those values into a calculator and we get that Z is equal to minus 0.5244. So this one's slightly more complicated. In this case, our area of 0.1 is above the limit of 29.0. So what we've got to do is find the z-score for the area of 0.9, the area up to this point. And you can see that the d value here will be less than 29, giving an area of 0.9. So if we put this into a calculator with mu equal to 0 and sigma equal to 1, we get a z-score of 1.2816. So I've written out the two simultaneous equations substituting both our sets of values into our equation for Z. Here are the two Z scores, 16.3, that limit minus mu over sigma, and 29 minus mu over sigma on this side. If you solve those two simultaneous equations, we get that mu is equal to 20 and sigma is equal to 7.03. And those are the answers.